Okay, so this is the slide from where we have to start, and it is about agents. In AI, our course will be, or our course will cover the development perspective and not the hardware, okay? So our course will focus on program development, okay? Smart program development, not on hardware like robotics or whatever, because we don't have any equipment here. Ah, so what is an agent? So in AI, agent is simply a program that you will develop. There are four things here which are highlighted in bold. So this is diagrammatical explanation, and this is the definition for the agent. What agent can do? Agent can perceive. Perceive mean observe, okay? Read or take input, okay? Agent can take input, agent can read, agent can observe, agent can perceive. So perceive what? Perceive its environment. The environment in which agent is working, in which your program will work, that program will have the ability to read from the environment, to perceive from the environment. And how our agent can perceive or observe? Through sensors, okay? Through sensors. Through sensors, your agent can read the data from the environment. And then after taking that input, it can process. And then after processing, it will reach on some decision. That decision will be a kind of action your agent has to perform on the environment. So that's why after taking the observation, after taking the input through sensors, your agent will act upon the environment. How? Through actuators. Through actuators. Actuator is what? Actuator is a hardware through which it can act upon the environment. So let's see this diagram. So this component is the environment, and then this whole block is the agent, and this white small block is the processing part, or is the processing part. Through this and this agent can perceive, can percept, which mean observe, read. So agent can percept from the environment in which that agent is working. It can take input from the environment through sensors. Then it will process that input, and after processing, it will reach on a decision, and then your agent will have the actuators attached with it. Through those actuators, your agent will perform action on the environment. So this is an illustration of the same these three lines that you have seen here. And this is the definition of the agent. This definition is more hardware related, huh? More hardware related. But it's okay. If it is more hardware related, okay, no issue. Because it is AI, and AI, you know that mainly there are two branches: robotics, or you can say that hardware side, and the other side is the operating system for that hardware. Okay, And that operating system, we call it in AI expert system. Okay, expert system of that hardware, or program of that hardware. You can simply say program of that hardware. And totally, this concept is called agent. Anyhow, this is the definition of agent. So now moving next, let's see an example of this agent. We are going to take, I have started the recording or not? I don't think so. Yeah. Yes, yes. That's good. So, uh, uh, so let's see the first simple example. And this is an example of a vacuum cleaner that you normally may have in your homes or at your homes. So this is automatic vacuum cleaner. Okay, this is automatic vacuum cleaner. So before going into deep in this example, first see what is the background. So this vacuum cleaner has two locations, square A and square B, as you can see here, square A, square B. And then this agent, which the name of the agent is vacuum cleaner, and this agent can perceive its location, can perceive its square, either it is square A, either it is square B. It can perceive, and perceive means read, observe. So first it will perceive that where it is, and then it will perceive that the dirt is available in which square. Okay. So basically, your agent can perceive the location and the dirt. So, for example, here some dirt is displayed on in this picture. So your agent can perceive the location, either it is in A or B, or it can perceive that the dirt is available or not. Okay. And then your agent can move left or right. If it is in A, it can move what? Right. If it is in B, it can move what? Left. It can suck up the dirt. Or if there is no dirt in both the squares, then what it will do? It will do nothing. So these are the actions. These are the actions of your agent. And these are the percepts of your agent. Okay. Percept is one thing, action is one thing. Okay. Now, simple agent function. What this agent will do? What is the function of this agent? What this agent will do, or what is the function of this agent? So now this is the logic of the agent, that how it will work. So your agent will see whatever the location is. We are calling that location current square, current location. And your agent will see that if the current square is dirty, then it will suck up that dirt. And if there is no dirt, the agent will move to the other square by taking the action left or right, whatever. So this is the function of your agent. Okay, the pictorial representation is here. You can see the agent is in square A and the dirt is available. Then it will do what? It will suck up the dirt. If there is no dirt, the agent will move to what? Right. And if this situation is happening here, the agent will move towards the left. And if there is no dirt on both the squares, it will do nothing. So 4 actions are available. So we can initially, not now. Initially, when there was not too much advanced programming languages, in the beginning, the people were doing this thing. The people were performing this action through these table entries. Through these table entries, they were building table. And in this table, we have a percept sequence on one side and actions on another side. Percept sequence means the percepts, the observation, the readings that your agent is taking with the passage of time. Before 1 hour, it takes, okay, the location is A and the location is clean, huh? So this is the location and this is the status of the location. Before 1 hour, it takes a percept that location is A and it is clean, and it perform the action, anyhow, leave the action. And now after 1 hour, it is perceiving again, and it is perceiving that, okay, location is A and the status is dirty. So or leave this example and take this one. And after 1 hour, it is perceiving that this was the previous percept before 1 hour, and this is the current percept. It is again perceiving that the location is A and the status is clean. So these are the two percepts in a row. So two percept means percept sequence, okay? And when you have a single percept, it is single. It is simple. It is only a percept. So when percepts will be connected with each other, like you can see here, so this is called percept sequence. And overall, we are calling all these entries a percept sequence. Okay, anyhow, leave it. So I am telling you that in the beginning, when there was no advanced programming languages, and then when there were not too much development facilities, so at that time, people were handling these things with the table design. They were designing table for that. And in the table, we normally, for this example, we have two columns, percept sequence and actions. What it means? So initially the agent is perceiving, and the agent is perceiving that the location is A and the status is clean. And if the location is A and there is no dirt in it, what will happen? The action is what? Move towards right. You have to write these entries in the table. And similarly, location is A, and these four entries you have to initialize in the table first. And if the location is A and the amount is and the dirt is available there, then what? The action is sucking. And similarly, if location is B and the status is clean, if location is B here and the status is clean, then what? Move towards left. And status is B, location is B, status is dirty, then if dirty, then sucking. So if these four entries will be in the table, you have to initialize the table with these four entries. And then what happened? Your agent will go again in the environment. And if your agent, and it will perceive, and if your agent would be in square A, and if the dirt is available, and if it is in square A and the dirt is available, then it will match this entry, A and dirt. It will match. A and dirt is this, huh? A and dirt is this. So then what? Here it is not mentioned, but then what happened? A, dirt. Okay, sorry for my writing because I am using mouse. And then now the current is what? Again, A and the dirt. I am writing only D, which is this one, this current percept, which is this one. So this is the previous one, which is this entry, and this is the current entry. And when A and the dirt, then what is the action? Suck. So it will, what will happen? This is the current percept of the agent. It will match this current percept with these entries. It will match this entry. Okay, this is the previous one, and then it will write the next entry, and then it will take the same action here. What is the action? Suck. So it will take the same action, sucking. So if you This is one way. Other way is you have to write all possible entries. This is first time. This is second time, and so on, and so on. This is first time perception with single entry. This is second time perception with two entries. One is previous one, old one, and then last is current one, and so on. This is the third time percept, which means these two previous two are the old ones. Current is the current. The last one is the current. Always last one is the current. And action is the same. Even for this, whatever the action is this, that would be the action for this last one. But this whole is called sequence. The other approach is you have to write all these entries. that would be that would be huge. You can understand with the passage of time, huh? And if you will write all the entries, maybe you will have one row with 100 percepts, huh? Maybe more than 100%. So, and then what? Whatever the current percept, it will match those entries, and where the row will match, it will take the action and it will perform that action in the environment. This is one approach. This is an old approach. This method is not a good method. This was in the history. What is the other method? To build a smart, intelligent program. Okay. So, and these are the three lines for that. And here we are writing the function for this agent. Okay, we are writing, okay, this is small algorithm, you can say. Function, and the name of the function is reflex vacuum agent. You can name it any. And what it will take, what parameters it will take? The location and the status. Two parameters. It will take up, this is percept, okay? This is what? This is the percept your agent will take through sensors. Vacuum cleaner will have sensors, okay? Your hardware will have sensors. Through sensors, it will take these two locations. Not location, two entries, two parameters, the location and the status. And then we are checking that if this status, if this status is dirty, then what action? We know. Then return suck. We are returning an action. We are returning this action suck to the agent, and agent will perform this sucking operation through the device, through the equipment which is attached with the vacuum cleaner. This is if statement, and then this else if is connected with it. So if status is equal to dirty is false, which means status is not dirty, okay? Status, which means status is not dirty. There is no dirt available. Then what? We are checking. Else if location is A, if vacuum cleaner, this is the vacuum cleaner. If it is in location A, then what? Then return action. What action? Move to the right. Return right. So move to the right, and then through wheels that they have, they can turn, and through that hardware, through those equipment, your vacuum cleaner can go towards the right position to this square. Similarly, if your location is also not A, if this condition is false, then here we are checking if location is equal to B, then return left. Then return left. So this small program is covering all your options which you have written already into the form of this table, which is not a good approach due to its size. If you will write all the entries, then the size of this table would be daunting. The size of the table would be huge. So this approach, writing smart program, is a better approach. And now this program is this algorithm you can code easily, and then it will work. And then you know that you can write all your programs on the chips through Z software that is available. If you have studied computer architecture or digital logic and design, in these courses, we normally write codes for the circuits, and then we normally write those code by using that C software in Z software in the lab on the chips on the ICs, and those ICs we can fix in a hardware, and with the wheels and all that stuff, and then it will work. Those ICs has the legs, and each leg has its function. One leg is taking input, other leg is giving you the output, and other legs are moving some right action, left action, or something like that. That chip is a program. Some program is coded in that chip.
Why repeat
Hmm?
Why we repeated the sequence?
You were sleeping when I said that. So this is the table, okay? This is the old approach. What people were doing at that time, people were writing tables with all the entries, with all the entries. So this sequence means these two are the previous percepts of old times. And now this sequence is the percept of current time. Okay. And if you will go like that, that's why and so on is mentioned that somehow at some time in your table, you will have some row with 1 million entries, you can say. If the lifetime of your vacuum cleaner is maybe you can say 1 year or whatever, then it can do 1 million percepts in 1 year easily. So then what? Up to 1 million entries in one row, up to 1 million percepts in one row, then you can imagine that your table, oh, well, you will say that I don't want to read it. I don't want to create it. If you have to write all the entries of that table by yourself manually, and then there is a one row in it which is going up to 1 million entries, it is hard for you to write all the entries. But initially, people were doing that. And then what? Okay, you can also do these entries up to 5, 6, 7, or 10, and 10 entries in one row, and then what? Reset the device. Reset the device again and again, huh? So anyhow, leave it. This is not a discussion that I want to do because these are the old time techniques. This is now the things which are available. This is now the thing which we will do now. Now, moving next. So in old times, people were writing that table with all the entries first, and then they are using the simple. They were taking the input and they were matching that input with the table entries, and if matched, then in the other column of the action, the action is available. They will fetch the action from there, and then the agent will perform that action. This is the old time approach. But now you have only 3 lines program for that. So now rationality. I told you normally rationality means something you will do logically and rightly. What is rationality? Doing the right thing. Okay. If I will give you the short definition of rationality, then it is what? Doing the right thing. So we want our agents rational. We want our agents to do the right thing. Okay. We want our agents rational. We want our agent to do always the right thing. And then rationality depends on 4 things. Then rationality what? Depends on 4 things if you want to achieve it. You have to address 4 things in the design of an agent. In the design of an agent, you have to address 4 things. What are those? You have to address the performance measure. Performance measure is what? It is a criteria, it is a formula that you will set in the programming of your agent that will define the success of your agent. What is meaning by success? That the agent has achieved the target or objective. If agent has achieved the objective, it is success. If not, it is not. So you have to define the performance measure in the design of the agent, and then prior knowledge. So when you are designing an agent, rational agent, okay, when you are designing a rational agent, you have to give the agent the prior knowledge, prior information before, before designing the actual thing. You have to give some information in the beginning, before actually running the environment. During the design, in the beginning, you have to provide some information about the environment to the agent. Okay, so you have to provide the prior knowledge of the environment in the design of the agent. And then actions. Actions, of course, your agent has to perform actions in the environment. So you have to define the actions of your agent, those actions that your agent will perform in the environment. So action is the third thing that you have to consider. And then percepts, input. So percept is input, action is output, and prior knowledge is something that you will give as an initial value. If you will relate it with a simple program, then you can redefine these different terms in your own words. So percept is input, action is output, prior knowledge is the initialization of your program or agent, and performance measure is that formula which will decide that your agent has done something good or not. So percept sequence from its title, you can understand that this is the input of your agent. This is the input of your agent. It can be one, and with the passage of time, it can be a sequence. Okay, sequence of percepts. Because when your agent will start working in the environment, initially it will have only one percept. After some minutes, it will take second percept. After some minutes, it will take third. So 1, 2, 3, 4, 5, and so on. So these percept from the first up to the end is called percept sequence or percept history. So percept sequence to date. So you have to also think about the percepts of your agent, and your rationality of your agent is dependent on all these four terms. And then what is the definition of the rational agent then? Now, by using these four terms, we are going to give a definition for the rational agent. We already have the definition for the agent. In the beginning slide, we saw the definition of the agent, and now we have a definition for the rational agent. By using these four terms, because these are the four terms on which rationality depends, so now we are going to give a definition for the rational agent. So that is easy. You can use these four terms. So when an agent select actions, action is what? This thing. On each percept sequence. Percept sequence is what? This thing. So we have an agent, and if our agent can select actions based on these percept sequences, and these actions, I want that these actions will maximize the performance of the agent. And this is now the third one, performance of the agent. We are using this. Only one is left, prior knowledge. Again, agent selects actions on each percept sequence, and these actions will maximize the performance by having the prior knowledge. then it is called rational agent. Leave these four terms. Use your own words for these four terms. And then you can say, if an agent has a percept sequence, and on that percept sequence, if agent is performing actions by using the prior knowledge, and if those actions are improving the performance of the agent, then that agent is called what? Rational agent. So you can use your own words, but you have to use these four terms, and then you will have the definition for the rational agent. Moving next. Here the topic is changed. P's. This is an abbreviation of something, okay? So what is P's? So P for performance, E for environment, A for actuators, and S for sensors. So collectively it is P's. Shortly we can say P's. Performance measure, environment is environment of the agent, actuators through which you can perform actions, sensors through which you can take percepts. So if you are going, why this topic? The reason is that if you are going to design an agent, then this is the first thing that you have to plan or that you have to define on the paper. Okay, so if you are going to design an agent, you have to define these four things: that what is the performance measure of the agent, what is the environment of the agent, what are the actuators of the agent, what are the sensors of the agents. You have to write them on a paper or in a table or in a list or anything. So for example, if we are going to design an automated taxi driver, automated car, automated taxi, without driver. So then what? Okay, then you can do some. What is the name of the agent or agent type? It is taxi driver, automated taxi driver. You can also write. And then what would be the performance measure of this agent? I want that when this taxi will drive on roads, the journey will be safe. Okay. I want that the traveling would be fast. These are the different contributors to measure the performance of your agent. Safe traveling, fast traveling, legal traveling, signaling, traffic rules or whatever. Comfortable trip, if the passenger is there, then comfortable trip. And then maximize profits, and also frequent traveling is needed so that it will earn more from the customer. So these are some points which you can consider for finally deciding about the performance of this taxi, that it is performing good or not. If it is not doing any accidents, safe and fast, there is no fines or whatever, and customer, when you will take the feedback from the customer, they always say that they are saying that the trip is comfortable and maximize profits. Mean if your automated taxi is doing frequent traveling and earning much. So these are the different things through which you can check the performance of your agent, and you can consider these things for this performance measure. And then environment, the second category. What would be the environment of this taxi driver? This taxi will run on roads, not in forests. So roads is the part of the environment. Other traffic, other vehicles is the part of the environment. Pedestrians, people who are walking across the road, pedestrians. And the customers who will be your customer, who will be the customer of this taxi driver. So these are some components of the environment. If you will think there are some more, you can also write them. This is just giving an idea. And then actuators. Actuators are those hardware components that will be the part of your agent. That will be the part of your agent. So here you are writing that steering is the actuator. Through steering, you can move left or right. Okay, this is the action that you can perform on environment. So that steering is actuator. Accelerator, accelerator for giving the race, huh? So accelerator through which you can increase the speed of your vehicle. So that is also you can perform action on the environment. So accelerator, brake, signal, signal, and then horn, and then display screen in your vehicle or in this taxi. So these all are what? These are actuators. These are you can say actuated. Through these things, you can perform your agent can perform actions on the environment in different states. Sensors, or you can say these are more close to your output devices, huh? Anyhow, sensors. These sensors are the equipment through which you can take the readings, the observation, the input. So cameras in your taxi is sensor through which you are taking input from the environment. Sonar. There are sensors normally on the bumpers of the vehicle. They can detect the distance between the taxi or the next object. Okay, so that is called sonar. Normally in the rear bumper, when you normally drive back your car, and if there is an object behind, then you will start hearing a sound inside, tin 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 tin, like that. So that sonar sensor is working there. So similarly, speedometer, which is showing you the speed, the GPS system, the odometer, the total kilometer distance, accelerometer, when you accelerate, the the needle moves, RPMs you can say, move on the RPM readings. Engine sensor, there are many engine sensors. And keyboard, it can happen that you have a keyboard in your car. So all these different uh, hardware components are the things which can give you the readings from the environment, which can give you the input from the environment. So these are the sensors. So this is how before before designing or not designing, before development of your agent. Development means software development. Okay, so before the development of your agent, first you have to think about the agent, and you have to define these P's. You have to specify these P's for your agent, and in this way you will have a plan, huh? In this way, so this is something related to planning. So similarly, this is a table. This is an agent medical diagnosis system, some medical equipment which can diagnose your diseases, huh? So, and the P's are written for it. Satellite image analysis system, satellite image taking images analysis system. So these are the P's for that. Part picking robot, a robot which is working on an assembly line on a belt, and it is picking that faulty parts on the assembly. So, and the P's is written there. Refinery controller, interactive English controller. So read it by yourself. This is not something difficult. Okay. Characteristics of P's. So specifying P's was that previous topic, and now properties of P's are categories, are characteristics of P's. Actually, here, characteristics of peas, actually, you will be more discussing the quality of your environment or the property of your environment. What type of different environments are available for your agents? This is basically the topic. So, our environment can be in any category. Here, first one is fully observable versus partially observable. This is the first CLO, so that's why it is something more theoretical. But from CLO2, it would be more algorithmic. Okay, it would be more algorithmic. Anyhow, so the environment of the agent can have different categories, and here we are seeing the first one: fully observable versus partially observable. Fully observable, shortly, when your agent can observe each and everything available in the environment, that is called fully observable. Okay, when your agent can observe each and everything available in the environment through sensors, that is called fully observable. And when your agent is not able to observe each and everything, each not able to observe each and everything in the environment through sensor, then it is called partially observable. This is the simple definition. This is the simple definition. And if your agent does not have sensors, then it means our agent does not have the ability to observe. So then fully observable or partially observable doesn't matter because your agent is blind. Huh? Your agent has no sensors. It cannot observe. So then these two categories does not mean anything for to agent. So this is what written here. If the agent sensors give access to the complete state of the environment, which means that thing which I said to you. If your agent sensor can observe each and everything of the environment, or can access complete state of the environment. Normally in environment, normally in environments, we will have different states. Your agent has to go into those different states. Your agent can go into these different states. And based on those states and observations, then your agent can perform something. Anyhow, leave it. We already discussed when I was discussing vacuum cleaner. Location is a state. Dirt is available or dirt is not available. It is also a state. Okay. Okay. If the sensors of the agent can access the complete state of the environment, then it is fully observable. If not, then it is partially observable. And then what would be the reason that your agent cannot observe the environment fully? The reason can be noisy and inaccurate sensors. If your sensor is now old and it can produce errors, huh? It cannot uh, it cannot read fully and accurately. And it is reading, but it is producing noisy data. Noisy data normally means its own technical faulty data. I will give the definition of noisy data later on when we will discuss some probabilistic model. Then you will understand it clearly. Because noisy data normally, when you are handling statistical models, then noisy data means something else. And generally, noisy means okay, something with a sound, huh? So leave this. But here you can say that if your sensors are inaccurate due to any reason, due to uh, uh, depreciation are due to, you can say your sensor is old enough, and then it is producing inaccurate, it is reading inaccurate data. So that can also be a reason. And due to this age of your sensors, it can also produce noisy data. Or if there are no sensors, if the sensors are totally missing from in your agents, then it will not read anything. Here example is given that if your vacuum cleaner agent, that the example that we have seen previously, if that vacuum cleaner has only a local dirt sensor, which means the agent, if your agent is uh, present in location A, it only knows that location. Okay, that means only local to that square A. It does not know that the dirt is available in square B or not, while your agent is present in location A. It does not know that the dirt is available there or not. That is local sensor. But if your sensor is probabilistic, then your agent, even your agent is present in location A, it can tell that the dirt is available in location B or not, because it is probabilistic. It will calculate that, it will calculate the existence of the dirt in the location B through probability value. Okay. Anyhow, simple. If your agent can read or observe or percept each and everything in the environment, that is called fully observable. If not, that is called partially observable. If your agent is observing something but not in full, then it is partially observable. If your agent is completely not observing anything, then it means something is, either the sensor is not available or something is wrong with the sensor. Huh? So that can then that environment would be what? Unobservable. Okay, unobservable. Now the second category, single agent versus multi-agent. Your environment can be single agent or multi-agent. For example, here single agent means single user, or multi-agent means multi-user. For example, if you have built a chess game, that then normally two players can play that chess game. This is what multi-agent. And if you have built another game, that is what crossword puzzle, in which you have rows and columns and some words and sentences are there with some missing letters, and you have to complete those letters either in row or column. Okay, this is called crossword puzzle. And that crossword puzzle game is what? A single user. Single user. Okay. So the environment can be single agent or the environment can be multi-agent. So from its name, it's easy. It's easy. If you want to explain its definition, then it's easy. Okay, single agent is done, multi-agent is done, competitive multi-agent environment. So the example that we have taken, the example of chess, it is a multi-agent environment, but it is competitive. Two players are competing with each other. Okay, this is what competitive, and yes, yeah, they're at the same time competitive. Competitive means competing, competing with each other. And cooperative multi-agent environment is what? That taxi driving or driving on the road is cooperative. There are many vehicles, multi-agents, and you have to, and your taxi has to drive and also cooperate with the others. If somebody wants to go ahead, you have to give him the way. You have to cooperate with him, with those agents or humans or whatever. So that is cooperative multi-agent environment. Okay, moving next. What is deterministic and stochastic? So this was the second category. Now third category, deterministic versus stochastic. Normally, I said to you that if for example, if this is the environment, and you can consider that this is the map of a this is not map, so this is a map of some country, and these are the different cities in it. And if your agent is what, your agent has to drive from one part to other part. Maybe your agent has to drive from here to here, and then what, these all other cities are, and including the starting point and the destination point, all these are what, states. And then if the path is available somewhere like that, then your agent can move from this to this, and then from this to this, and then from this to this. So moving from this city to that city is action. Is action, huh? Or, but for example, if your agent is moving from here to here, then moving from this city to that city is action. But this is the current state. And after performing the action, this is the next state, okay, on this path. So now you will understand this thing. Now you will understand these two lines. An environment in which your agent is on the current state, your agent is on the current state, okay? And our agent is setting navigation. And if your agent is on the current state, can determine the next state by considering the action between these two states, then that environment is called deterministic. That you can determine the next state. Next state. Again, your agent is at the current state. And if your agent has the ability to process that, if I will go from this city to that city, then where I will reach? The next city. Huh? If your agent can determine the next state from the current state by considering this action between them, then this environment is called deterministic. Otherwise, this second one, stochastic. Okay? Otherwise, stochastic. Stochastic is a term, normally people are using this term stochastic sometime with probabilistic, but mathematicians have different theory for probabilistic and different theory for stochastic. Anyhow, so stochastic is something statistical, okay? Something statistical. Or if I will go further deep in it, then it is a category in which the probability is involved. Okay? Probability is involved. So if the environment is partially observable, previously we saw what is fully observable. And here we are saying if the environment is partially observable, then it could appear to be a stochastic. Then that environment can be stochastic. If the environment is fully observable, then it is not the category. If the environment is partially observable, it means some states you can determine, some states you cannot. So then what? Then it would be stochastic, because the next state you can predict either correctly or not. The next state, because it is partially observable. If it is partially observable, then it means that the next state you can predict, your agent can predict. When I say you, it means agent. So your agent can predict the next state in partially observable environment either correctly or not. Then how we can solve this problem? Through stochasticity, through probability evaluation. That's why when, so for example, let's see this. If your automated taxi is going on the roads, your automated taxi agent cannot predict that what would be the traffic behavior exactly at some location. Your taxi agent cannot predict that when its tires will blow out. Your taxi cannot predict that when its engine will be seized up. So these are different states. Seizing up of the engine, blowing out of your tire are traffic behavior. Even you can predict that traffic blockage can occur at some position, but when normally we reach there, there's no traffic blockage. So anyhow, so these are some events which you cannot predict easily. So then what is the solution? Then if in the environment, if your agent is not able to predict the next state properly, then the environment is stochastic, and here different things can happen. And you can now solve the situation in stochastic environment by calculating the probability values for those events. And then you can decide that the traffic can be blocked at some point, or the tires can blow out, or the engine can be seized up. You can calculate this event by probability values. Anyhow, sometime environment can be uncertain. What is I think ghair yaqeen?
Yes.
Okay. So environment is uncertain. Sometimes environment is uncertain. When the environment is uncertain, then again it is not fully observable. Then it is again, it is what? It is not fully observable. And if it is not fully observable, it is not deterministic. So when the environment is uncertain, it means that you cannot calculate something which is in the next state, which is in the next state. You cannot, your agent, you means agent, you cannot calculate that next state accurately if the environment is uncertain. Then what? Then here again in this situation, you can calculate those next states through probability values when there is uncertainty. So these type of environments would be called stochastic environment. And the uncertainty about the next outcomes, the next outcome that you will calculate in this stochastic environment, you will calculate these outcomes or next states through probabilities values. So that's why if your agent is calculating some probability values, then you will say that it is a probabilistic model, that your agent is probabilistic agent. We will see different types of agents. What is non-deterministic environment? Deterministic is one in which you can determine the next statements, and the environment in which you cannot determine the next statements, next states, then it can be non-deterministic. But in the non-deterministic, what it means that you cannot identify the next states. You cannot calculate the next states. But if you are calculating probability values to calculate the next state, then it is not, then it is stochastic environment. But if you are not using the probability values to determine the next states, then it is non-deterministic also. Again, deterministic is what? Where you can determine the next state. If you cannot determine the next state, then it is non-deterministic. In the non-deterministic, if you are not using probability values, then it is non-deterministic. If you are using probability values, then it is what? Stochastic. Now, the next, episodic versus sequential. Episodic is a word from episodes. Sequential is a word from sequence. So, what is episodic environment or task environment? This is an environment in which your agent experience is divided into episodes, or you can say this is an environment in which your agent will do some task in episodes. Okay, in episode, and in each episode, your agent will take a percept, and then based on this percept, it will perform a action, and then you will reach on the next episode. And the quality of this episode task environment is what? The next episode does not depend on the previous episode. The next episode, you can say the next step does not depend on the previous step, and we are calling that step a episode. Or you can also call that episode a state. Okay. So the next state does not depend on the previous state, you can say. But here the word is episode, so use that word. And now sequential. Sequential environment, the current decision or the current state could not affect all future decisions. Could affect all future decision. So sequential environment is the opposite of episodic. Is the opposite of episodic. Here, in sequential environment, one state is dependent on the other is on the other is on the other. So states depends on each other, or you can say the next state is dependent on the previous state. That is the true sentence for this sequential environment. Next state is dependent on the previous state. Chess and taxi driving are sequential. Example is there. If you are playing chess, your one move and the future move is dependent, huh? Similarly, taxi, moving from one state to another state. If I want to move from Medina to Makkah, first I have to go to maybe the next city, Zulashira, the outskirts of Medina, and then like that, I have to go there dependent, and then on that route.
But welcome cleaner example is episodic.
The next state is, for example, location A, location B. So location B, you want to clean it. It is not episodic. Episodic, yes, you can, because the episode does not depend on each other. It is episodic, not sequential. For example, if you want to clean the square B, it is not necessary that you have to clean the square A. Okay, so you can move toward the square B first, clean it, and then you can come back. So the states are not depending on each other. So that's why you can say episodic. And for episodic, the example is there, but I didn't mention. Sorry for that. So this is the example here for episodic, that if your robot is working on a assembly line, on a belt, and it is picking up faulty or defective parts which is coming on the belt, and if that robot is picking up the faulty parts. And now one part appears before the agent, and the agent has picked it up. And this episode does, and if the next part is coming, this is one episode, next part which is coming, it is another episode. And this episode which this agent has done by picking it out from the belt, it does not mean that the next part would also be defective. Okay, so that's why this episode does not depend on the next one. When that part will come before the agent, it will observe again. If everything would be okay, it will let it go. If something would be wrong, it will again pick it up. So that is the example here written here, but that was missed by my side. So now, environment can be static, environment can be dynamic. So if your environment, if the states in the environment is changing when your agent is working in the environment, that is dynamic. If your environment is not changing, it is as it is, so then it is static. Discrete and by the way, I have written read it by yourself. So read it by yourself, okay? Because these are not difficult things. It is only the matter of reading. When you will read, then you will understand. So these are like news, News. So anyhow, discrete and continuous, I can give you just simple idea. Discrete environment is an environment in which you will have different states and unique states. There is no repetition of state. Okay, that is called discrete environment. And continuous, in which, for example, the values 0, 0.1, 0.2, 0. The state is what? 0 and 1, and then 2, and then 3. But between these states, you have 0.1, 0.2, 0.3. So some continuous values. Similarly, known or unknown environment, if everything is known, this is like fully observable, okay? If everything is known to the agent about the environment, that is known, otherwise unknown. These are some examples now. Crossword puzzle. Crossword puzzle is what? Columns and rows, and you have to fill the letters. Some letters are there, and you have to complete the words, either in rows or columns. So that crossword puzzle. Now this is, if you have built that game, so now this is an agent, crossword puzzle. And it is now you have to tell that it is fully observable or partially observable. Crossword puzzle is a small game. And if you are an agent, think you are an agent, and you are seeing all that crossword, it is fully observable or partially observable? If it is in front of you, fully observable means when you can see all the states of the environment. And if that puzzle is in front of you, you can see each and every cell with all letters. So it is fully observable, not partially observable. That the thing which is hidden, you have to complete it. But the states which are in display, all are in display. And this crossword puzzle is a single agent or a multi-agent? Single player game, So that's why it is a single agent. And this crossword puzzle is deterministic or stochastic. Deterministic means when you can determine next state from the current state. And stochastic means if you have to calculate the probability value to calculate the next state. So what? Crossword puzzle is a deterministic or probability. If these puzzles, you have solved these puzzles, I think many times, rows and columns. So you are seeing the sequence of the letters, and then you can predict what would be the letter next, And here you are not calculating any probability values to predict the next word. Huh? So that's why it is what? Deterministic. Because you can determine the next state from the previous state. You can predict the next letter from the previous letters, huh? By considering the sequence. And now crossword puzzle is episodic or sequential. The sequence of the letters is dependent on each other or not. If not, then episodic, and if it is, then it is sequential. So then it is dependent. So that's why it is sequential. The crossword puzzle is static or dynamic. So whatever the environment is, rows and columns, the letters which are there, you cannot move the letters here. Whatever is written there, that is there. And the cells which are empty, which you have to predict, and that is also fixed. Okay, that is also fixed. One or two different solutions are possible, but it is fixed. So that's why the environment is what? Not changing. It is fixed environment with fixed states. So that's why it is static. Static, not changing. This crossword puzzle is discrete or continuous. Between the states, is there anything involved between the states, or the states are different and unique? So each block is different, huh? So that's why it is discrete, and there is no further hidden states involved between them. Similarly, the chess game, it is fully observable. You can see all the 8 by 8 cells, huh? So fully observable. Multi-users, multi-agent game, deterministic. You can determine the next state from the current or from the previous state. Okay, if you are moving, you can determine that I'm going next, huh? Because if when you will move, then you can determine, okay, these are the possibilities for the other players. Nothing more than that, huh? So you can determine. So episodic or sequential move depends. Whatever the move you will do now, your future movements are dependent on it. So that's why sequential. Chess is a static or dynamic. So with the moves, your paths can be changed, huh? Your paths, your future paths can be changed. So it is neither static, not fully dynamic, because the fixed possibilities are there. So it is semi, in between. Semi means in between. So it is not Arabic semi or Sami. Okay? It is semi. Semi means in between, both. Semi means static and dynamic both. Okay? And discrete or continuous. So fixed number of possibilities. So that's why fixed number of states. 8 by 8, and you can multiply all the possibilities, then you can say that this number of movements is possible, huh? I cannot tell that how many, it would be long, huh? So, but this discrete, fixed number of movements, that's why discrete. And similarly, you can read the other things by yourself. This is the poker agent, this is the backgammon game, this is taxi driving, medical diagnosis, image analysis, part picking robot, refinery controller, interactive English tutor. And I will start next from here, inshallah. This is section 7019. Huh? Okay.